Alcohols, they do behave as acids. They are not strong acids. They are weak acids. And the hydrogen here is going to be the weak acidic hydrogen. The reason why it's an acidic hydrogen, because of the oxygen that is connected to it. So we said that the definition for acidity is when the acidic hydrogen is connected to an electronegative element. So that hydrogen is going to be partial positive due to the electronegativity of the oxygen in there. And the oxygen is going to be electron negative. So the more partial positive the hydrogen is, the more acidic it is. So alcohols, they do act as acidic compounds, and this is the first reaction that they undergo whenever they are present in presence of a base. The base, if it is a strong one, it's going to come and take the acidic hydrogen every single time, and you're going to get the base of the acid. This is the conjugate base of the acid, which we call here the alkoxide. So this is the alcohol, this is going to be the alkoxide. It's an oxide because it's an O with a negative charge. Normally, if it's a strong base, that base is a negative charge, so it will have a positive counter ion to balance it, and that positive counter ion will balance the oxygen. These are the examples of all the bases that I can use. Notice that OH is not one of them. We can use the hydride, the amide, the alkyl lithium, the alkyl magnesium bromide. We've talked about this type of base, and we said that the alkyl magnesium bromide is simply an R, which is connected to the magnesium by a covalent bond, and then the bond between the magnesium and the bromine is an ionic bond. Now, the magnesium is 2 positive. That is going to make that R partial negative in there. Now, for simplicity, for these types of reagents, which we call Grignard reagents, this bond is a covalent bond. But for simplicity, we're just going to disconnect the R from the Mg and make the R in there having a negative charge with a lone pair. Is a covalent bond with the Mg. This is a simple representation of the Grignard reagent in there. So this R is going to be our base. The bond between the R and the lithium is ionic. So anyways, that R is going to be our base. So we can pick the bases in there. As you can see, all the bases are strong bases because they are negative charges. So whenever you have a base, the base immediately will come and take the acidic hydrogen and form a negative charge on the oxygen. Now, if you notice, OH is not found in these bases. The reason why, because OH is a weak base to take that weak acidic hydrogen. This is a weak acidic hydrogen. To take that acidic hydrogen, it needs to be a strong base to come and grab this hydrogen. But OH minus is considered to be weaker to take that weak acidic hydrogen in there. So OH minus here, compared to the other bases, it is a weak base. So that base is not enough in strength to come and take that weak acidic hydrogen. So this is why the reaction is going to be slow, unless the alcohol that you are starting with is a phenol. In this case, this hydrogen will be way more acidic than this hydrogen here. And the reason it's more acidic because of residence in the phenol. So this one is going to be more acidic. Then the OH minus can come and take the hydrogen and create the phenoxide. The first reaction, these are all examples in here. The first reaction that our alcohol undergoes is an acid-base reaction. And in fact, acid-base reaction is the most important reaction in organic. Whenever a strong base is present and an acidic hydrogen is there in the solution, this is the first reaction that happens. Base comes, takes the acidic hydrogen. Every time we make a bond, we break a bond. So now you're going to end up having a negative charge on the oxygen. So again, the idea here is to pick your base. And our base here is going to be the R in the Grignard. So we said that the R in the Grignard, we're just going to express it as an R with a lone pair and 2 negative charge just for simplicity. Although the bond between the carbon and the Mg is not ionic, it is covalent. So the Mg is always expected to be connected to the carbon, but we're going to break the bond in there and just show the CH3 alone. So that base is going to come, take the hydrogen, and you're going to end up getting your CH4. And then throughout the process, the magnesium is going to break down, and then the magnesium is going to balance the charges of the oxygen and the bromine. With OH, the reaction will not happen. Pay attention, this is not a phenol. This is a cyclohexanol. So this hydrogen will stay weak acidic. So a weak base cannot come and take this weak acidic hydrogen. These two are strong bases. So the base from the carbon, so you have to locate your base from the carbon. This is a negative charge. So that base is going to come from the lone pair and attack the hydrogen, or the hydride from the sodium hydride is going to come and take the hydrogen and form a negative charge on the oxygen. You're going to get your product. In all the cases, your product is going to be a conjugate base and a conjugate acid. Bases vary in there. So these are the examples of the different bases. I can have a different type of reaction now if I use the POCl3. Now, what is that? You have to draw the Lewis structure for the POCl3 in order to figure out that phosphorus is a Lewis acid. Why it's a Lewis acid? Do the electronic configuration of phosphorus, you're going to see that it still needs electrons in its p orbital. So in this case, it's going to act as a Lewis acid, and Lewis acid will take electrons from a Lewis base. Now, instead of this hydrogen being acidic, the oxygen is going to now be the base, and the phosphorus site will be the acid. So now I'm having here a Lewis base, Lewis acid reaction. It's not like all of these reactions in here where I am ending up having a Bronsted and Lowry base with the acidic hydrogen, which is the Bronsted and Lowry hydrogen. Or I can say this is a Lewis base with a Lewis hydrogen, Lewis acid hydrogen in here. Now this is the opposite. The oxygen now is going to act as a base, and the phosphorus is going to act as an acid, Lewis acid. Whenever you have a product of the Lewis base and the Lewis acid, your product is always a complex. The lone pairs are going to attack the electrophilic site, which is the phosphorus. One of the chlorine is going to leave, and you're going to make a complex in there, and the Cl-, which is going to be a leaving group.